Hey guys, it's Vince. Today in this video we're going to be discussing Ferrites and when are they best used for your CNC robotics application. I get questions now in excess easily of 70 times a month on when can I use a Ferrite in substitution of double shielded cable. Of course, we see the simplicity of it. You've seen many of my systems. I get all the time told, hey, I've watched your video on the Raptor builds and the Pro builds, and I see how you incorporate Ferrites in there, and how can I do that on my system, and can I just substitute per se on like a double shielded spindle cable using one and just use Ferrites on a regular cable? Can I get away with something like that? And the thing we have to realize is that Ferrites are very, very good passive filtration only based on specific distances. They are not to be used in long distance over duration because, again, the impedance will change. And for proof of this, what I wanted to do, again, I like hands-on. I could tell you guys all theory all day, but we're all hands-on. So let's look at this in a more forensic term. Fair-Rite's a corporation who manufactures Ferrites. They've been around a long time, and we also know that they've really pioneered a lot of the different designs we see. I personally love their brand. I love Kemet. I love TDK. There's tons of different brands out there to fabricate different types of Ferrites for different types of applications, whether it be for PC use, whether it be for automation use. It does not matter. We also see them used a lot of times in audio because noise is noise as far as EMI. So what they cover in this video, which is why I want to cover it and I want them to explain it, is you can see a first-hand experiment of using different wire lengths and what happens when he takes actual precision lab measurements on the effectiveness on the impedance to see exactly how these units work and to understand better how to apply them to your system. What you'll notice in my builds, and when I cover it in detail, is all of my builds have Ferrites, and usually it's going to have multiple Ferrites spaced at a certain distance. Well, finding that distance is actually pretty easy to do, and it's just understanding, once again, the size of the Ferrite you're using, the specs it's using, and again, understanding what's available in terms of solutions for your EMI issues, especially with CNC automation, because again, they certainly make your build much simpler. However, and I want to state this before we play the video, there is no substitution for understanding double shielded cable is a tool that must be used with every system if we want the best stable robot. There is no way around using it because, again, it mitigates both forms of EMI in the high and low frequency, on top of the fact that it incorporates full length of the cable transition. So you're not going to get noise penetration variance over any specific length, not 6 inches, 7 inches, 10 inches. Ferrites can also be used on top of shielded cable if we want to drop impedance even lower than that. I don't recommend it. You're not going to see a tremendous difference for our applications. Once again, we're not trying to eliminate all noise. We're trying to drop it to a level that is not going to interfere with our signal reception on our precision electronics for control. So now that I said that, we're going to play this video, and I want to warn you guys, keep your sound up because I am not in control of this video's audio. It's very low. So I'm going to do my best to boost it with my audio editing software, and I'll see what we can do. But again, the engineer does an exceptional job of showing firsthand Ferrites in terms of how they're used with different lengths of cable and what to expect when using them. So check this out.
Some electrical team leader at Fair-Rite Products Corp. This is going to be a video illustrating the effect that test lead length has on the rated impedance values of the Ferrite suppression device. So a little bit about our test setup today. We have a Agilent E4991A RF impedance analyzer along with a 16092A spring clip fixture. The part we're going to be measuring is a Fair-Rite Products 264300801 shield bead. It's a round bead focus, approximately 7.5 millimeters in diameter, 7.5 millimeters in length with a 2.25 millimeter aperture. We're going to be running impedance curves from 1 megahertz to 1 gigahertz. We're going to be using 4 different wire lengths. So we're going to be using a 25 millimeter wire length, which is our standard wire length that we use for a part like this. A 51 millimeter wire length. A 102 millimeter wire length. And a 152 millimeter wire length.
Now again, guys, he is naturally adjusting the wire lengths. We're going to see that. Just to give you an idea, naturally, this is a smaller magnet ferrite. The larger the ferrite, the more effectiveness it will have on a larger cable in terms of length. But again, the whole idea of this video is to show you the perspective of how effective a ferrite is, regardless of its size, used on a length of cable and how it varies so much from different lengths.
So first thing we're going to do is our cable through the core and connect our shield bead to the fixture. And now we're going to trigger a sweep. So we see a plot here of impedance over frequency. And we have 4 markers set at frequencies that correspond to our typical listed values for this part. So those are at 10 megahertz, 25 megahertz, 100 megahertz, and 250 megahertz. So you can see the impedance values that we have here roughly match what we list as typicals. So we, at 10 megahertz, list 42 as a typical. At 25, we list 63 ohms as a typical. 100, we list 92 ohms as a typical. And 250, we list 109 ohms as a typical value. So now for comparison, let's see what happens when we increase the wire length to 51 millimeters. Connect our part. And trigger a sweep. So the 10 megahertz and 25 megahertz values haven't really changed very much. The 100 megahertz value has gone up by a few ohms, and our 250 megahertz value has jumped by almost 20 ohms roughly. So let's see what happens if we go up further still to 102 millimeter wire length. Part connected, trigger sweep. So now we're starting to see a little bit of an increase at 10 and 25 megahertz, though still fairly comparable to what we had with the original test lead, the 25 millimeter. The 100 megahertz now nearing 30% increase in impedance, and the 250 megahertz we are nearing double what we had originally measured with 25 millimeter wire length.
It's amazing how fast you could see that curve come up. And you can see those frequency changes, especially at the higher ones, guys. These are the questions that I get asked the most, when am I going to see a spike? How long a lead can I use to get away with? And now you see how the actual ferrite becomes ineffective the longer the lead gets. And we're going to continue this, but I wanted you to pay close attention to these numbers because you're going to see it take a big spike, especially with the arc here. Look at this as this is going up. It's pretty intense.
So just for the sake of an example, let's put an extremely long wire on here, 152 millimeters. Let's see what happens.
Okay, that's 152 millimeter wire, and the stock wire length is 25 mil with that actual ferrite. So when he jumps up to something like this, picture a spindle cable for your application, and picture whatever size ferrite you're using. There's no way you're ever going to get full signal protection. You will have an isolated signal protection, but nowhere near what's required for a cable of this length. I'm going to hit play and you can see the results yourself. Now, in all fairness, I want to point out one other thing you guys may have noticed. If we just come back here a teeny bit of when he places this on, you can see how much room is around the ferrite in terms of extra space, because the ferrite itself is a much greater diameter of the hole than the actual lead he's using. We still see it working, but the tighter the ferrite is, the more powerful the magnetic field will be around your actual casing of the lead, and that will make it more effective as well. So again, I always highly recommend, he's just doing this for experimental purposes. The principles are the same, but I always recommend using a ferrite that's properly sized with an inner diameter very similar to what you'll be using with your actual conductors, because again, the tighter the fit, we want to penetrate the casing to give us that magnetic field in as strong and a possible sense as we can get. So I'm just going to hit play here and we'll take it from there. Look at that spike.
So the results
Look over here
are getting pretty dramatic. So now we're increased at 10 megahertz a fair amount, 25 megahertz we're up over 10 ohms from where we were originally. The 100 megahertz we had about a 50% gain from what we originally had measured, and the 250 megahertz we're more than triple. So
again, very, very high spike overall. We just seen it's almost non-existent as far as filtering.
Original values. So just for a little bit of fun now, let's test the impedance of just the wire with no part attached whatsoever. Trigger. So the 10 megahertz value is fairly negligible compared to our original values that we measured. The 25 megahertz is fairly substantial. And interestingly, the 100 megahertz value with just the wire, no part attached, actually nearly matches the typical listed value for this part. The 250 megahertz is still nearing triple what we had originally measured for the coil.
Now, I think it's amazing to discuss the fact that, let's see if I can get back here, that he actually is showing the part without a bit, or I should say a bare lead without the ferrite installed, and where he's at about spec for that wire at the 100 megahertz frequency without the ferrite. So it's interesting to see where you actually have a negated effect where you're at a point of no return, so to speak, due to length, and we see that the effectiveness of the ferrite can actually be negligible, where you're installing it and you're actually better off using bare wire. Now, how would you know this if we just based everything on theory? That makes no sense if we're thinking just in theory. That's why I say engineering is more hands-on than theory. You might have a theory that you put into practice, but until you test physically, see the variables firsthand, then you find out things like this, which, again, even the engineers sound surprised. So, again, very, very interesting to see this video. And again, I hope it's making it clear for you guys out there who are thinking about using ferrites over an extended length of cable. It's just not practical, nor is it safe, again, for system stability.
So really, if you're looking for more impedance, just get longer wires and traces on your circuit. No Ferrite needed. Just kidding. One more issue with having wires this long for testing impedance is going to be repeatability. So let's put the trigger on this back to a continuous trigger, and just moving the part around, you'll see the effect that this is having on the measured impedance values on here. And this would create a massive headache for our quality department.
Now see what he's doing, and I want you to pay very close attention to this. He moved the ferrite on this end, then prior to that he moved it over here, and you can see right here what's happening to that graph, how we're moving all over the place. And this is very similar to what would happen if you applied a ferrite in a specific location over the length of a cable and didn't have another one to follow up with. And that's the whole principle of this. If you were going to use a long lead, the best way to use it would be to actually use it with another ferrite following behind within an applicable length. So for instance, when you see my step and direction Ferrite cables, where I actually install Ferrites on the cables, the length has been predetermined. If we do not do that, we're going to basically have what we have here, where we only are filtering in a certain location, and you can see once again on the graph how effective it is. So if we were to put a Ferrite here, let's say a Ferrite up here and one over here, or increase the size of the ferrite and only put two ferrites, maybe one over here and one over here, this graph would be much, much more stable. And again, still be highly effective. It's when you have long cable runs, like you'd see on a 10-foot or a 20-foot spindle cable, that's where you're going to have issues, because again, you're running multiple conductors inside a casing, and then we're hoping to get the magnetic field inside the casing over the entire run of the cable, and then you have to run that cable typically inside of a cable chain where it's going to be automated. How practical would it be, and logical would it be, to have those clamped onto the cable where you have automation going back and forth? That explains why that's never done in robotics, because there's no way for it to be a sensible applicational use, because again, those ferrites would be under constant friction. It would be causing constant friction for whatever cables are inside the cable chain, and it's just not practical for end user capability. So what we're looking at here, using the ferrites, again, it would have been interesting to see him put a ferrite over here and a ferrite over here and then see the graph, because I'm telling you right now, you would see a dramatic difference. But these are interesting points that he's bringing up, and very easy to fix. If a cable is a short lead like this, once again, put a ferrite. If it was small like this, we put one here, one in the middle, and one over here. If we use a larger ferrite, depending upon its effectiveness, we could put one here and one here, and just keep an eye on the length. The length is going to be key. However, once you get to a point of no return, and when I say a point of no return, typically when you see ferrites installed on cables that are for computers, let's say your mouse, you'll see the ferrite installed at the point of entry on the USB end of the cable, let's say if it's a USB mouse. And the reason that is they are using shielding on the opposite end of the cable. Again, it's usually a double shielded cable, and therefore the reception on that is going to be more linear at the base, but they want the end of the cable to be filtered. No different than you see on my DB9 EMI filters when they are used on DB9 plugs for the end of your stepper motors, because we all know the leads on a stepper motor are very short and they don't come with shielded cable. It's a very easy way to filter your signals on a short length. So again, short length, we're good. Longer lengths, not practical over most applications. And if it is a longer length that is going to be identified more for a stepper application or a servo application where we're dealing with step and direction signals, or any communication signal for that matter, if it's 12 inches or under, and I always use that 12-inch ratio, so like 300 millimeters for my metric guys out there, that's usually going to be your sweet spot. And again, utilizing the proper size ferrite, whether it's longer, shorter, in actual diameter and also length, and also looking at the size of the magnetic field. Again, that's what's going to tell you overall the best application. Of course, conductors. If you have a single lead like this, it's totally different than if you have 6 leads of a cable. So again, this is where the engineering factor comes in, and where you really want to know about the details, because they, like we saw here, and I'm not the one actually teaching you this. I'm showing you this in a live demonstration. I'm grateful because Fair-Rite did this themselves, and as a manufacturer, again, they're showing you firsthand what you can expect. So I think we can all learn something from this, and I hope it's been a help. I'll let them finish up.
Having wires this long and readings this inconsistent during testing. So the big takeaway from all this is to just do your research.
Now see, that's a very interesting point he made, because again, it's all variables. And you guys always say, God, you're so detail driven. You heard from another engineer how detailed they are. I mean, variables in application, positional use. You'll also notice on my Ferrite cables that they're locked in place with heat shrink. And the reason we do that is, of course, we want to make sure that that Ferrite's not going to move from position. It's a stable position because that's where it's most effective. So when you use proper heat shrink, it's going to naturally go over the Ferrite. Number one, it adds an actual protection barrier to the Ferrite, but on top of that, it's also locking it in position at that point on the actual lead. So again, very interesting to point that out, and something that a lot of guys don't even think about. They think, oh, he's just using heat shrink. There's a reason we're doing that. Okay? Now what he did with that test, again, it's just for example. But the idea is to keep that Ferrite in a direct correlated position so that it's most effective for your application. So again, guys, I hope that this video has been helpful. I hope that you've learned something out of this, and I hope you've understood now why Ferrites are an amazing resourceful tool to use during your build for your CNC automation controller. However, they have their place. Short wire runs, golden. Golden opportunity. You don't have to deal with ground leads. We don't have to deal with headaches of different sorts. When we are dealing with double shielded cable, we're trying to get into flexible areas. And there are tons of different types of Ferrites. You can get them in sheets. You can get them in donuts. You can get them in little torrids. I mean, there's just tons. Most of the ones I love are the snap-on type, except the ones I use in my Ferrite actual leads, and those are special 18-gauge Ferrites. Again, diameter plays a huge role. You can have them custom made. I get asked that a lot. If you decide to have that done, you can contact the company like Fair-Rite and discuss with them, minimum order quantity to see what you need for your systems as far as if you're doing, contractual builds. But overall, you now have a real thorough understanding of how Ferrites are to be used and how to use them properly with your systems. So again, if you have any questions, and I know videos always, I say in every video I think, they always generate more questions, sometimes more than answers. Please message me direct at storm2313@gmail.com. You can also message me through my eDealer store. You'll see links in the beginning of the video and at the end. I thank all my subscribers for your support. The channel's growing like crazy, and I love you guys for that. I can't say thank you enough. Take care.